Mm. Good afternoon, everybody. Hi. Mark, will you just make sure that everyone's admitted who's waiting in the lobby?
100%. I'll do that, Gabby.
Okay. Amazing. Thank you. I'm just going to wait 1 minute so that everybody can join us, and then we will begin our session. Okay, I think I'm going to get started so long. So good morning, everybody, and welcome to the Circular Lunch Club. Today we're going to be talking about circularity in the energy sector. I'm just going to share my screen quickly. Mark, can you just let me know that you can see the screen?
Yeah, I can see it. Perfect.
Okay,
yeah.
Fantastic. So welcome, everybody. Just to give you a quick overview of what a lunch club is, it's a short duration session. We're here to create an ongoing conversation around the circular economy in South Africa. It's also a platform to meet and for you all to have informative, accessible, and informal discussions. So my name is Gabriella, and I'm going to be your host today. I'm part of the team at CSA, and I'm very, very excited to have Dr. Frans Smit from Northwest University joining us today, who will be talking about a circular economy framework for refurbishing end-of-life solar panels. And just before that, I'm going to get into a quick introduction about CSA and an overview of circularity in energy. And after Dr. Frans presents, we'll have some time for Q&A. So Circular South Africa is a platform that amplifies the potential and value of the just circular economy across South Africa. And the circular economy provides South Africa with a regenerative alternative to our current take, make, waste system. So there are 4 fundamental principles in the circular economy. The first is designing out waste and pollution, then keeping materials at their highest value, regenerating natural systems, and benefiting all members of society. So the circular economy also provides a cross-sectoral systems approach where opportunities across sectors are interconnected. I think we'll see that today, where energy connects to mining and manufacturing. And then just to quickly talk to you about Circular South Africa's focus sectors for this year. We've got these 7 that we've identified, and so far we've tackled mining, human settlements, mobility, and this month we're doing energy. We're super excited also for the coming months to talk about water, agriculture, and manufacturing. So here's an illustration. It's part of our science communication campaign where we are talking about circular economy opportunities in energy. And what you'll be able to find here is information about the four different principles. And all of this information has been taken from the CSIR's technical report launch. And you can access this on our Knowledge Hub. But just to jump into energy and contextualize everything, a circular energy sector promotes decarbonization through the implementation of renewable energy technologies while ensuring that product lifecycle design incorporates energy-efficient technologies, maintenance, and repair. So circular energy involves 2 key ideas. The first is renewable energy utility. So this is generating energy through renewable and regenerative technologies. So solar is one of them, but there's also wind energy, hydropower, and some consider green hydrogen to be a part of this as well. And then the second is circular energy materials. So this is about designing technologies like PV panels and wind turbines with high quality materials, as well as increased longevity. Now, it's quite interesting because renewables require many more metals and minerals compared to conventional materials. And this then has an implication on mining. So recovering these materials and minerals from those technologies becomes super important. And then just to quickly talk about solar, when I was looking at the CSIR's report on circular energy, I found that they said that globally, solar PV modules are expected to generate up to 78 million metric tons of waste by 2050. So when this technology reaches its end of life, which is usually 25 to 30 years, we don't actually have the waste management infrastructure to deal with it. So what they also found in the report that in South Africa, there are only 2 recycling facilities that currently deal with all of this waste. So then what becomes important is that we need to manufacture components that can be easily repaired, disassembled, or recycled, or are less toxic and reduce disposal and ensure valuable materials stay within the economy. And this is something that I'm very excited for Dr. Frans to speak to today. And then just the last point is that there is a massive potential for African countries to become renewable energy manufacturers. At the moment, we import most of our renewable energy, and it's quite interesting to know that almost $1.6 billion worth of imports of solar PV modules are coming into Africa in 2024. So shifting from exporting our minerals and metals to actually manufacturing them is an awesome opportunity. So now I am going to hand over to Dr. Frans Smit, who will be talking to us about a circular economy for refurbishing end-of-life solar panels. Over to you, and really excited to hear about your work.
Thank you. Good afternoon. Can you see my screen?
Yes, all good.
Okay, and I'm audible?
Yes.
Okay, thank you very much. Yeah, so welcome. As Gabriella said, that I'll be talking about the circular economy framework for refurbishing end-of-life solar panels. And this presentation will not be as technical as you might expect, but rather a more positive outlook on what we can do to improve the circular economy of end-of-life solar panels. So Gabriella did touch on this, and for me personally, the circular economy for solar panels means that it's an industrial and social technical system designed to keep solar panel products, components, and the critical materials they contain at their highest possible value and utility for as long as technically and economically feasible. Now, the question is, how can we do this? How can we rethink, redesign, and repurpose for further panels? All right. So if we look at the redesign, we can redesign the hardware for easy separation and repeat use. Secondly, we can shift to responsible source and lower income impact materials. And thirdly, we can plan for end-of-life recovery from the outset. So taking this together, we can design for disassembly, sustainable supply chain and closed-loop recovery infrastructure, create a module that is longer lived, easier to refurbish, and ultimately feeds its components like glass and metal and polymers back into either new panels or higher value applications. Now, this is only on a manufacturing for new power solar panels. So the effect of whatever we do now will only be seen in roughly 2045 to 2050. So the question becomes is, how do we make an impact specifically today and in the near future, the next 5 years? Because as have been said, is that South Africa does not have recycling capacity. The two facilities that is available actually doesn't recycle. They only take off the aluminium, they strip the junction box and so on, but the real valuable products, which is 60% of the cost, is not recycled at this stage, because we don't have any of the infrastructure in place to actually recycle panels. So we are looking at about roughly 7 gigawatts connected at this stage, slightly lower, but more or less, which means that taking a 500 watt panel, it's roughly 14 million modules, 500,000 tons of waste that we currently have. And so we expect within the next 5 years, anything from 50 to 80 tons of waste. That's now only till 2030. But as you can see on the graph, this becomes exponentially a bigger problem because of the increased uptake of solar panel over the past decade. And therefore, the circularity is not only a future-orientated design issue, but rather, what do we do with the fleet of we already own and the waste that will accumulate before recycling plants are ready? So we have a 5-year window to actually implement this, and with the low amounts of waste that we currently have, the economics just doesn't make sense to have a full recycling line. So the question of how do we make an impact today rather becomes, how do we win time and manage the imminent e-waste stockpile? But luckily, we have the solution. And therefore, I'm proud to introduce to you SolaGro, where we literally make the sun grow. We do this by tapping into an underutilized spectrum of the light. So the UV range is not utilized by the conventional silicon-based panels. They rather utilize the visible light and some of the infrared light. So thereby, we can down convert UV light through our technology and have blue light available, which, by the way, UV light is also available during overcast periods. So you have a two-edged sword. Not only do you have technology that can increase your solar panel efficiency when it's sunny, but you also can decrease your intermittency on a panel. So down conversion is not a new technology per se. So there are quantum dots and rare earth dope materials. Those two specifically rely on either very costly metals. They are not readily available. They have a major economic or environmental impact, or they are toxic. Then complex organic dyes, again, very difficult to synthesize. They're not that cheap. They're not that stable because they all are prone to radical induced degradation, and therefore cost and sustainability have limited market uptake of these specific down conversion technologies. But with SolaGro, we avoid expensive and unsustainable rare materials by using an aliphatic organic compound to do all the heavy lifting for us. So in terms of the chemistry, this is basically the whole scheme of how we can, with very different routes, come to the specific compounds we are looking at. Now, interesting, the alpha olefins, which is some of the feedstocks that we are using, is a byproduct of the petrochemical industry, a low-value product that is currently 85% is exported to other countries and beneficiated there and re-imported into South Africa. So this technology not only underpins the circular economy for solar panels, but it also leverages the Fischer-Tropsch feedstocks. And this is arguably one of the single most compelling circular economy lever that this technology actually has to offer. So like I said, that our compound or our technology have the ability to down convert visible light into blue light, and therefore we can utilize this in various aspects. This is now only the solar application, and if you embed this in a polymer, you can produce a polymer sheet that can be put on top of a solar panel. And this is not only for end of life cycle that will increase their efficiency, but you can also put this onto new panels, new installed, currently installed, and end of life solar panels. We can also tune the wavelength that we have by combining or changing the chemical structure. You can get anything from violet to blue light to yellow, green, depending on what the emittent wavelength that you need. So these sheets are then placed onto this is just some of our preliminary results for the solar simulator. And what we have now seen is that with a film that is a solar panel that is covered with the film, we get about a 10 to 12% increase in watt output in the lab, which is significant. To put this into perspective is that globally, the trajectory of increasing solar panel efficiency has been roughly about 1% every 5 years, with $500 million spent on that 1% increase, right? So that is the average over the last 2 decades. So our technology, like I said, specifically works by utilizing UV light. UV light basically gets converted into blue light, and you have the panel that can utilize it. On top of this, an added benefit, actually 2 added benefits, is that remember that when it's overcast, you still have UV available. So not only does it increase a panel, whether or not it's new, whether or not it's end of life, it increases the solar panel efficiency, but it also decreases intermittency for solar panels, and therefore can improve solar uptake. And then, and additionally, because you have a laminate a polymer that you can relaminate a panel, you can now also seal micro cracks into a solar panel, and therefore extend its lifetime even further. So just to step back about the unique value proposition of the alpha olefins, there is a huge oversupply globally of roughly about 1 million tons of these alpha olefins available. 85% of all the olefins that is produced in South Africa are exported and beneficiated elsewhere, and then re-imported at extreme cost. And therefore, this technology also looks into how can we beneficiate the South.
Hi, Frans. I think we lost you for a second. And Mark, I just want to check from your side that you've also lost the audio of Frans.
Yeah, definitely lost the audio.
Okay. I just want to wait a sec. It seems like he's chatting.
He's still talking, yeah.
Can you?
Yes,
We can hear you.
I think you're
Okay,
back
so-
now.
Sorry about that. I didn't change anything, so just let me share my screen again.
Thank you.
Sorry,
I
can you
think-
just indicate where
Yeah,
was the last slide you listened?
yeah, you were on unique value proposition, and I think you were just about to talk about the cost base.
Okay, 100%. So what adds value to these or is a unique value proposition for the South African market is that the Sasol streams is one of the lowest value olefins on the world market. And it's not because of the poor quality, but rather it is because of the Fischer-Tropsch process, which is much cheaper to produce these olefins. So South Africa is in a very unique position to take advantage of our natural resources. And then because Sasol is here, we have long-term security, because it is projected that these alpha olefins will reduce within the near future. However, the SA market will stay, because Sasol have indicated on numerous occasions that those feedstocks will at least be available for the next 30 years. So we have long-term security in terms of our raw feedstocks. So our process, no, it doesn't want to, okay. So our process delivers circularity on two fronts. It's upcycling of surplus Fischer-Tropsch alpha olefins and extending PV module life, thereby closing both the resource and the e-waste loop simultaneously. And another question is, why the solution path? So there are several other pathways of increasing solar panel efficiency. So you can upgrade materials, you can control light flow, you can minimize reflection. All of those technologies is very incremental, and it works on the architecture of the solar panel, which is not efficient for a currently installed panel, or a panel that is becoming the end of life. However, if you extend the absorption window by a retrofit technology, it will be disruptive, and it can be applied to a wide variety of markets. So currently, our core tech is split into three different segments. It's the R&D, which is based at the university. And there we obviously do new research, new development, optimization of the system, looking into different polymers. How can we do that? And that is just the technology development. Then we are also looking at the market readiness. And interestingly enough, is that about 70% of all startup companies fail purely based on they did not do their market analysis or market research correctly. There simply isn't a market for it, and they have not developed the market. And therefore, within the first 5 years, most startups fail solely based on the market readiness. And then what goes hand in hand with that is the enterprise development, and that is the business structure, the governance, the human capital needed to run the plant, etc. And all of this is underpinned within my team, and also underpinned by several patents that we filed last year, a few articles that has been published on this work. And basically, we will now move over to the national phases, filing the patents at the national phase. So this technology is now protected under this. So just to come back also to something that I said, that remember now, if you have UV down conversion, the application for now is only solar panels, but we have identified several other places where we can utilize this. The solar panel market itself, or the application, is definitely one of our biggest one. But a very interesting application would be here at the advanced photosynthesis, because if you can convert UV light into blue light, and blue light specifically is also one of the well, blue and red is the only light spectrum that plants utilize. So if you increase the UV of the blue light into a vegetable tunnel, for example, you can increase your yield, you can decrease your crop cycle, and therefore increase food security. Depending on the structure of our compound, we can also produce compounds that absorb UV, but it doesn't emit it. And there is other applications, for example, as new sunscreens, where the current sunscreens on the market all have either is environmentally unfriendly, they are toxic. Most of the organic ones are also prone to radical-induced degradation because of their extended aromatic structure, and therefore there are no options in terms of the cosmetics. So this technology really extends far beyond only solar panels. There's a majority or a large sector of untapped applications that we are currently looking at. And that's all from our side. Thank you. This is just to show our team. I'm the group leader. Some of my co-workers and students working on some aspects of this with some of our previous funders. Unfortunately, at this stage, we actually don't have any funding. So yeah, if you have a few million in your back pocket, please get in contact with me. I will gladly talk to you. Thank you very much.
Amazing, amazing. Thank you so much. That was super, super insightful and amazing to see how many applications this technology has. So we're going to open up the Q&A now. But I already see there is one from Joan, and it says, Frans, regarding the design for disassembly, how is the film removed from the panel? Is it solvent or is it manually? What happens if it breaks?
Okay, so the technology at this stage is only at a TRL level 4. But the film that we do are, well, actually investigating at this stage, it can be dissolved. So at a later stage, yes, you will be able to dissolve the film. The polymers as well as the compound itself is also biodegradable. So it also, we're looking into that, and our compounds does not contain any metals or any extended aromatic structures. It's fully biodegradable. So when you are reaching the end of life of that film, we have already engineered those properties into the film.
Awesome. I hope that answers your question. If anybody else has questions, you're also welcome to raise your hand and we can unmute you so you can have a chat with Frans. I've got another question from Mark, who's asked, would it be possible to explain how this technology can be used for the majority of waste modules that have broken glass or damaged cells? I'm not sure if I missed this.
Yeah, so the technology would not be able to save broken panels at this stage. It's only to extend the life of either panels that is becoming end of life. So I was at a conference about 2 years ago where I met actually the guy that is the manager of one of these recycling plants in KwaZulu-Natal. And what they do is currently they don't buy the panels. You pay for the panels to be recycled by them, and they don't recycle it. They only remove the aluminium, the junction box, and so on, and then it's shredded and put into the ground. So, I mean, the amount of waste that we expect from a broken glass or damaged cell is much less than the waste that we will expect from the normal cycle of end of life. So these will extend the life extend the life of roughly about 5 years for a panel. But it will because it also can be retrofitted into existing panels as well as onto new panels. Everything will then basically shift downwards, and this basically just gives us time to prepare for the masses that we are expecting.
That's great. Thank you. I see somebody has, someone raised their hand. Oh, there's Aisha. I'm gonna, I think you should be able to unmute, Aisha.
Yeah. Thank you so much. This is really exciting tech, and I really hope that you find those millions somewhere. I wanted to ask you about job creation within this process? What is your foreseen kind of job creation within the application of this tech? Is it quite easy to implement, and therefore people don't have a huge barrier to entry in terms of skills needed? But yeah, I suppose that's on to you.
Yeah, so definitely our philosophy was when we started with this process is that we wanted to create something of value created by South Africans in South Africa for South Africa. And although, yes, it is internationally, I mean, South Africa actually only have 0.5% of the global market of solar panels, but definitely you are looking at, first of all, there will be a synthesis plant where you will be employing anything from normal factory laborers to more specialized roles, chemical engineers and chemists and so on. Then there is the packing, distribution, the marketing, sales, the application of the film, because this is now retrofit, so you will have installers, and those companies can either be registered within us, or it can be a third-party company that can effectively also create jobs. We're still busy with that's part of the market readiness. One is looking into exactly how many jobs there can be created. But to give you a ballpark figure, on a small plant that can only service about 10% of the South African market, and again, only 5.5% of the solar panels are in South Africa. So we're looking at least 25 people that needed to run that plant, and that's excluding the marketing, excluding the installers, excluding distributing, and so on. So there is a real possibility of creating a substantial amounts of jobs, especially once we scale and go internationally.
Thank you. This sounds amazing, and hopefully go regionally as well, look towards our neighbors.
Thanks.
100%. All right. Any more questions? Any more hands raised? I'm gonna give it 1 second. I actually have a question. What is the lifespan of the SolaGro currently?
Okay, so the exact figures we don't know yet. Like I mentioned, we need funding now to do that segment, to actually take the technology to the next level. We are now at the product development phase, so we don't know, but based on the polymer lifespan and so on, it seems to be roughly about 7 to 10 years. I see there in the comments, Mark, do you only recycle the solar panels or the cabling, transformers, inverters as well? Is there economic value? So I'm not sure who's asked this question, but basically, remember that we are not specifically looking into the recycling of this. We are looking into how can we extend the lifespan of a solar panel. And because you can apply and reapply this film, take it off and put it on again. Effectively, you can, I'm saying 5 years, and that is our target, but it can be much longer. And so solar panels itself degrade because of UV that degrades them, right? So if you have a film on top, which actually converts all of the UV, there's no UV degradation of the solar panel. And that's additionally a property of our film, is that there is no UV actually getting into contact with the silicone wafers. So we don't know yet. That is part of our ongoing research. I'm actually heading to Europe next week, where we will have hopefully very interesting conversations with the several PV institutes in France, as well as in Belgium and in Germany. I've got several meetings with a lot of these key players with them to see how we can integrate their access to technology and funding into our work, hopefully to better our technology.
That's so exciting. Good luck with all of that. I've got one more question from Tulani, which I'm not sure if you have an answer to it yet, but they've asked how much would it cost on average? And then I think after that, I'm going to wrap up the session.
Okay. Yes. So the cost also, because we are still at lab scale, is at this stage, no, we can't, we can't say, oh yeah, there's a panel that will cost you this much. Our preliminary investigation actually shows that we will most likely be able to produce these films roughly for about 150 Rand per square meter, which sounds significant compared to a panel which is roughly about 10%. But even only if you get an absolute 2% increase out in the real world conditions, it leverages about 9 gigawatts of additional energy on a 1 megawatt plant. So the payback period is literally 2 years.
Awesome. I think that's a great answer. Okay, guys, I'm going to just wrap up this session very quickly. Thank you, everybody, for joining us today for this lunch club, and especially thank you, Frans, for telling us about all of it. Please, if you can, rate our lunch club. This really helps to support us, and connect with us, follow our channels, get onto our website, become a member, become a partner. We'd love to chat to you and connect with you, and see you at the next lunch club. Thank you, everybody, so much for joining.
Thank you very much. I'm going to leave my email also in the chat. If anybody wants to contact me, you're more than welcome to send me a mail.
Great. Yeah, and we'll send everybody an email with the presentation and Francis' details.
Thank you very much. Appreciate it.
Thanks, guys. Cheers.
Thanks, guys.
Enjoy the rest of your day.
Cheers. Bye.
Bye.